We want to include different kinds of variables, and we're going to have a bit of a ball with the categorical variables, because they are sort of a nuisance and difficult to interpret. Okay, we can have anything there. So interval, we will not look at ordinal for now, but interval and categorical are the only ones that we're going to distinguish here. So let's see what we have in our data. We have in our data a religion. I must admit that I do not really have an argument why I would think that you commit more or less traffic violations based on your religion, but nevertheless, let's give it a try. In the data we have here 9 categories. Let's see, we have, sorry, this is in Dutch, we have I'm not religious, I'm Roman Catholic, Protestant, other Christian beliefs, Islamic, Hindu, Buddhist, Jew, or other religions. I'm not sure what that would be, but there you see, well, that for the example here, it's not so convenient to have 9 categories. So the first thing that I'm doing here is I'm bringing this back to 5, just to make it a bit more convenient to work with. And what I'll do here is get rid of the ones that have the least. So what I'll do is recode this command over here. For religion, all the 1s stay 1, all the 2s stay 2s, all the 3s stay 3s, and the 4s stay 4s as well. But 5, 6, 7, 8, and 9, I recode to a 5. So all the ones Islamic, Hindus, Buddhists, Jews, and other are now plunked together, with my apologies for any religion who feels bad about being too close to these other ones, but just to make the group a little bit larger. And that generates in this case variable that's called religion L5. That is the new variable that I want to work with here. And then it looks like this. This variable has 5 categories with, let's say, a decent number of persons in each and every category. And what I also did is I created a variable label like this, label var L5, in which I already mentioned what the 1, 2, 3, 4, and 5 actually mean. That makes it easy, because then if I ask for a tab, then I do get this label in there, and I do not need to check anymore what is what. Okay, now, what are we going to do? If I have something like this, where in this example I have 5 categories in the variable, what I do is I create 5 dummy variables, 1 for each religion that I have, where dummy variables are defined in the following way. I create a variable that's called religion 1, that's equal to 1 if the religion type is number 1, and otherwise it is a 0. So perhaps, let's say a little bit more convenient in terms of the label would be, I have to check what was the first one again, none. So I could also create a variable here that's called none. None is 1 if religion is 1, and 0 otherwise. I do that for all 5 categories. So now I have 5 dummies, 1 for each of the different categories, and I now add 4 binary predictors to the regression equation, not 5. 1 less than I have categories. And for the same reason, in fact, as I used for the male-female example, there we have 2 categories, we include 1 dummy. 1 dummy for 1 of the separate categories, in that case it was female, and the other one is then automatic, because that's the only category that we have left. It's the same here. For 5 categories, as soon as we have 4 defined, then we know, yeah, the other one is already in there. And we will see that there's some trouble in terms of interpretation, where the interpretation of the coefficients was relatively easy for interval variables. It's a little bit different for the other ones. Now first, let's see how to do it in Stata. There are different ways to do it. These are only a couple, there are more actually. This would work. I do a tab, and then I ask for generate R. Now I get 5 variables, R1, R2, R3, R4, and R5 in my data to do that. That second, or that thing I could do as well by typing separate commands here. R1 equal to, and then a logical statement. The religion variable equal to 1. Whenever this is true, you get a 1. Whenever this is not true, you get a 0. So this one and that one deliver me exactly the same thing. Or if you are into for loops, at some point somebody asked that can we loop around something here? Well, that will work too, because this set of statements you could also write like this. For values I equal to, from 1 to 5, curly brace to the left, it has to be there, not on the new line. And then a curly brace right, actually there, all the way after all the commands that you have. And then you can type all the commands that you want to run for different values of I, and the only thing you have to take into account is this over here. And this is not a typo. The thing on the left of the I is a my keyboard that's on the top left, and the one on the right here is a single quote right, so really another quote, and that is simply putting in the number I. So the first run through the for loop, this will be a 1, and there will be a 1, you get that command, and you do each and every one of them in the same way as you had above. Or there's still another way to do it, and it is type the command xi and I dot really L5. Okay, will also work. Okay, anyhow, here we see this happening. First, this is why I actually do this and leave out. Now, I've created these R1 through R5, I leave out R1. You can leave out another one as well. I'll show you what happens when you do that. But first, let me just include these and have a look here. Also note, by the way, that what I did here, the variable is called dangerous. I typed danger and not dangerous. That'll work as long as there is only one variable in the data that starts with these 4 letters. Then Stata will understand, apparently that's the one you're aiming for. Female as well, if there is another variable in the data that starts with FEN, then this is not going to work and Stata will complain. But in this case, we're fine. Let's see, what did I want there? Yeah, have to tweak a little bit. What would happen if you didn't know that in this case you need to include 4 instead of 5? So if you just put in 5, then Stata will complain. Note, R3 omitted because of collinearity. So if Stata throws one out, I'm not exactly sure what the rule is that Stata uses on which one to throw out. You could throw out any one. In this case, Stata chose to throw out number 3. But in any case, you'll see something like this. And the thing to remember is, first, you have to, you have to see this, you have to take this into account and know what it means. This in all likelihood means that you have included one dummy too many. And in principle, it doesn't hurt, as long as you are okay with the fact that this is there and that you have now nothing here and know how to interpret all this. The results are not wrong, but it could very well be that you didn't mean the R3 to be left out, and instead wanted the R1 left out. And the only way to do that is then by hand. Let's see. Yeah, okay. One thing that I haven't in the slides here, but that I should mention, is that you can do this wrong. In another way, if you simply forget about the fact that this is categorical, then you could, instead of these R1 through R5, you could simply include that rally L5 variable, which is coded 1, 2, 3, 4, 5 as well. So if Stata won't complain, it will actually give you back results, as if that rally L5 variable is interval scale. That doesn't make any sense. It's not possible to interpret it anymore. If I increase 1 in terms of religion, or whatever that would mean a change from, let's say, not religious to Christian or something, then I do get an effect on my nonsense. But the thing is that you have to take into account that you don't do this, because Stata doesn't know how you want this interpreted, and you'll get back a result as if that variable is interval scale. And that simply makes no sense at all. Okay, so let's see once more. This is the part of the output where you only see coefficients here. Basically, what all these models do is, well, they say, if you tell me what female is, what kilometers per year is, what R2, 3, 4, and 5 is, then I will give you back a prediction. Okay, so for any case of the data now, we could actually predict what will be going on. And the thing that we need to consider now is, well, how do we interpret these kinds of values? The first one we knew already, okay, for female, on average, given all these, that we can profile all these, the value is half larger. For kilometers per year, an extra kilometer per year gives me a little bit extra, but now these are 2, 3, 4, and 5s. Okay, these dummies are slightly different. Let's see. What do these deliver? It's actually slightly different from the female case as well. So for R1, what do we have? Well, if we predict, let's say, for males who drive 10,000 kilometers per year, we could come up with any other example, what do we have? Well, 1.09 is the constant over there, plus 0 times the minus 0.5, 0, because we are looking at males here, not the females, so this coefficient doesn't enter the equation, plus 0.196, that is 10,000 times this coefficient, plus, and then what? 0, because all of these, for category 1, R2 is 0, R3 is 0, R4 is 0, R5 is also 0. So none of these coefficients enter the equation. So my prediction in this case is exactly this number. I didn't calculate the actual number, but this is how I would calculate it. Same thing for each and every one of the other categories. So for R2 I could do the same thing, and everything would be the same actually, all the way up to there. And the only thing that would be added now is minus 0.0778, that number over there. Because for R2, I'm in the second category, now I have a 1 over there, and I need this coefficient and need to subtract that. Same for R3, 4, and 5. I can get predictions here for each and every category that you want me to deliver. How do we interpret these numbers? Well, the only way to interpret them is not by saying, okay, here we see that R3 has an effect of minus 0.19 on Y. That's not the way to interpret this. And you can see it from the numbers over here. For instance, let's stick to the R2, this is the first one. The minus 0.0778, that's exactly the difference between R1 and R2. Okay, so that number over there says something about the extent to which R2 differs from the category R1. Same for that number. This number says something about how R3 there differs from R1. And that goes for all the coefficients. So the coefficients for a categorical variable that we have split up in this case, 4 different dummies. All these different dummy coefficients say something about how the actual categories that we have over here compare to the one that we left out. Okay, so this is why it makes a difference which one you exclude for the interpretation of these coefficients. In this case, we're comparing this with R1, which is left out. If you would have left out R3, we get all the coefficients that resemble, okay, compared to R3. Okay, for here, that I think works, and I think I have an example here. Yeah, exactly about this. So let's see. Now we do this twice, once with R1 left out and once with R2. Now let's see what happens. First, we see that everything that is about the fit of the model doesn't change. Okay, so in terms of how well your model is doing, it doesn't matter if you leave out 1, 2, 3, 4, or 5. It's all the same. Also, it would be weird if that would be the case. The data didn't change at all. The other thing is, if you look at the coefficients, not of the separate categories that we're talking about now, but of the other variables, so the female and kilometers per year, also no difference. Okay, so if you switch the category that you leave out, for all the other variables there is no effect whatsoever. However, there you do see differences. You see that R2 is only in the top table anyhow, but R3, for instance, is minus 0.19 in the top table and minus 0.11 in the one on the bottom. And this I have a bit bigger here as well. So here you see, in fact, that even though all these numbers here are different from the ones over there, that these results are, let's say, internally consistent and basically give you the same model, even though all these numbers are different. Okay, so we have the difference between R2 and R1. That is that number over there, minus 0.078. That is what you see over there. And we have the difference between R3 and R2. That is this number over there, minus 0.11. That totally consistent with each other. For instance, here R4 and R3, the difference is, well, minus 0.19 versus 0.20, which is in total 0.3896, calculated based on these numbers. Or I could calculate this on the right side. R4 and R3, well, here minus 0.11 versus 0.28. So that difference is also 0.3896. Okay, so what happens if I use another category that I leave out? Basically nothing much. For most of the variables, it doesn't make a difference. For the dummy variables themselves, it does make a difference, but the interpretation of the model and the model, in fact, itself is exactly the same. All right, so does it make a difference? Answer, well, no. It's exactly the same model being estimated, but you do see some different values, and the different values you only see as coefficients of these separate dummy variables. All the other ones do not change at all, and for the comparisons that you want to make, you simply have to decide for yourself with which of these categories you want to compare. Let's see. Yeah, a couple of side notes here that are good to have. This is what I already showed you a couple times. This is still another way to do it. There is a stata command or stata tweak, so to speak. If you put an I dot in front of a variable, as we did over there, then what you get is output that looks like this. You tell stata by the I dot in front of this that, okay, what I want is separate dummies for each and every one of this variable. And if you're not interested in the dummies themselves, you don't want to use them later on in your analysis, it might be good enough. The only disadvantage is, again, here stata will choose the reference category for you. So here 1 is left out, obviously. 2, 3, 4, and 5 are still in. But if you do not mind about that and simply want to check what happens if you include this variable, then this could work as well. Let's see. Yeah, so the difference is for the thing on the top there, you have to do it manually yourself. Tab, religion, comma, generate R, and then you get these different R's. And at the bottom you don't have to, but then you also do not get the dummy variables in your data. Okay, once more, here we do get a reasonable argument why we would use the test command after using stata in one of these regression analyses. Here I left out R1 once more, so again, same thing in the regression table. Now you could argue that I can now not see if there really is a difference between R3 here and R4. This one has a minus 0.2, this one has a plus 0.2. Might be a difference there, and it turns out, first of all, that I can test this like this. Test R3 equal to R4, and then I find not rejected, supported. So it looks like perhaps there might be a difference here between category 3 and 4, but in the end, it turns out not to be the case. Finally, another test command that is typically useful if you want to test here, did it help at all? Oh, I see I made a typo over there. Did it help at all to include the religious variable here? Because the religious variable is now creating 4 of these dummies. And if I want to know something about, okay, do all these dummies taken together help the model at all? Then there is a way to test it, yeah, but it's not this one. What I should have typed here, R2 equal R3 equal R4 equal R5. I would like to type here equal R1, that's the one that I left out, and I know R1 is 0, so I should type here equal to 0 after it. And then you get a test, a joint test. How likely is it that all these R values add something as a whole to the data, or stated differently, H0 would be all these coefficients are 0. If that would be the case, how likely would it be to get the data that we have? And in this case, we'll see that, well, this is actually supported, suggesting that indeed these religion categories do not add anything to the prediction of how many traffic violations that you create. Let's see, I have on a separate slide the do file that I